Hello guys, today we'll be starting with the topic of hybridization, right? As we all know, it's a very important topic from the views of NEET, JEE as well as your board exams. So let's get started, alright? Now, the question arises, why are we studying hybridization? What is the need of hybridization, right? So let me make you understand with the help of an example. Let's take the example of methane, that is CH4, right? If we look at carbon's electronic configuration, let's look at that. Carbon's electronic configuration would be, this is your 1s, 2s, and this would be your 2p, alright? So what is its electronic? This is 1s, this is 2s, and this is 2p. Alright, so 1s2, 2s2 and 2p2, right? This is carbon's electronic configuration in ground state, right? This is carbon's electronic configuration in ground state, mind that. Now we will look at the carbon's electronic configuration in the excited state. What would that be? What would we do? We cannot do anything with 1s. Why? Because these are not valence shell. We can only use the electrons which are present in valence shell. Alright? So what would happen? 1s will remain as it is. And what will happen with 2s? And this would be 2p. Right? So the one electron from 2s will jump into 2p in the excited state because these are both valence shells, right? So here, here and here. Now you would say, ma'am, we need to make CH4, right? We have 4 unpaired electrons. We need to make 4 bonds. Then it's done, right? It's done. Then, but no. You will have one SS overlap from this. You will get one SS overlap. SS overlap. And from these 3, you will get SP overlap. Right? But now it is seen experimentally, practically, that CH4, all bonds of hydrogen with carbon are identical in all aspects. Their strength, their length, their energy, everything. So why is it so? If this is the actual scenario, then 3 bonds should be identical and should be at 90 degrees. Why? Because Px, Py and Pz, they all are mutually perpendicular, right? But it is seen that all the hydrogen-carbon bonds are identical. So, to rectify this problem, Pauling introduced a concept that we are going to study, that is hybridization. So, this is the need of hybridization, right? Secondly, hybridization is a totally hypothetical concept, right? But why are we studying it? Because it can explain the geometry of compounds, right? It is very successful in explaining the geometry of all these compounds, all these polyatomic compounds. That's why we are going to study it, right? Now we get to understand what is the need. Now let's talk about what is hybridization, right? So now we'll see what is hybridization. Now let me make another illustration for you. Suppose we need to make mango shake. Hybridization is just like mango shake. Trust me, it is. Alright, so what is it? If you need to make mango shake, what will be the ingredients that you will need? It will be milk, sugar and mango pulp, right? Now you can tell which quantity is present and what amount of these ingredients are present in the mango shake. But once you have turned the mixer on, you have made your mango shake, Alright, now you can tell what will happen. Now you cannot tell if you take a sip of your mango shake that which sip includes more mango pulp or more milk and whatsoever, right? You cannot tell that. So hybridization is the mixing of atomic orbitals to give a new set of orbitals, right? When you mixed them, they form a new set of atomic orbitals which have the same energy and same shape. They are identical. You cannot separate them now, which one is S or which one is P. You cannot do that, alright? Now, let me tell you what are the features of hybridization. First of all, the number of participating orbitals is equals to number of hybrid orbitals. Hybrid orbitals are the orbitals which are formed after intermixing. That is our hybridization. No, that's what it is. So this is the first feature. Now the second feature would be the hybrid orbitals are of equivalent energy and shape. Okay. Then the next question which is in my mind would be, so how are we able to predict the geometry of compounds using hybridization? See, now we have made the hybrid orbitals, right, which have equivalent energy, right? So what is the possible way of arranging them? What is it? You take the electron pairs and direct them in space such as to minimize the repulsion. That's the only way. It's just simply VACPR way. But here we are mixing the orbitals first, then we'll apply the VACPR to get the geometry of the compounds. Alright. If you are mixing 1s with 1p, so it will be your sp hybridization. If you are mixing 1s and 2p, then it will be sp2. Similarly, if you are mixing 1s and 3p, it will be sp3, and so on and so forth. sp3d, sp3d2, sp3d3, right? It works this way. Now let's move on to some examples. Okay, right, let me do some examples. Let's take CH4 first. Now see how can we rectify that problem which we discussed earlier. So it was our, or let me just take you to the back slide. Right, here it is. But when we moved backward, so after intermixing, what will happen? After intermixing, what will happen? We are going to mix these to this. We are going to mix these two orbitals. Alright. So what will happen? They will form an equivalent energy of orbitals. It would be, now you have 4 sp3 orbitals. 4 sp3 orbitals. One electron in here, one in here, one in here, and one in here. Now what would we do? Let's bring hydrogen. So where is our hydrogen? Here it is. Here is our hydrogen. One electron here, one here, one here, and one here. That's how our CH4 is formed. Alright. Now the problem of your SS overlap and 3sp overlaps, that problem has resolved. Now you have 4 sp3 orbitals which have equivalent energy and equivalent shape. So there is no such issues, and that's why the bond angle comes out to be 109.5 degrees. Alright. It's 109.5 degrees. Alright. That's how it works. Now let's work out some examples, and I'm going to tell you some tricks to find out hybridization. So let's move on. Alright. So now we have understood what is hybridization, right? Now I'm going to tell you a very short and super quick trick which is going to help you to find the hybridization. So let's get started. Let's take the similar example first. It is CH4. You just need to calculate the number of sigma bonds plus free lone pair. Plus free lone pair. That's it. That is it, really. By using this simple kind of, you can say, formula, you can calculate the hybridization. Let's take CH4. What is CH4? Carbon makes single bond with hydrogen in order to form methane, right? So the number of sigma bonds would be 4. There are no free lone pairs, so it comes out to be 0. So it comes out to be 4. Then the hybridization is sp3 simply, and the shape is tetrahedral. It is fixed. Whenever your hybridization is sp3, the geometry is definitely going to be tetrahedral only. Alright, I'll give you a short note on that as well. Now let's talk about BeCl2. Beryllium has 1 lone pair in its outermost shell, right? So what would it do? One electron will make the bond with Cl and the another will here Cl. In BeCl2, the number of valence shell electrons that beryllium has, it is 2, right? So it is just simply going to be 2. No lone pairs, so 0. Here the hybridization would be sp, right? Now let's take the example of NH3. What happens with it? It has 5 electrons in its outermost shell, right? 3 will make the bond, that will be sigma bond, right? So 3 is here and 1 free lone pair, right?